Guys, how's it going? Mike coming back at you here with another video on vector calculus. In the previous video, we did a couple more examples of differentiating or finding the derivative of some differential forms. We got some more practice with those properties of differentiation, and we saw an important result regarding the integral of a differential 2 form. And what do the dx, dy, dy, dz, and dz, dx mean in terms of our parameterization for our surface? In this video, we're finally going to get to that big theorem. We're finally going to tie together all these theorems that we had learned about, not only in this course, but theorems we had learned in previous calculus courses as well. So let's just get right into it, guys. We're going to kick it off with Green's theorem. Now that we're armed with the knowledge of differential forms and how to take the wedge product and how to differentiate these things, we're going to look at Green's theorem in this new light. So we're going to first look at the hypotheses for Green's theorem, which for the most part are going to be the same thing, but we're going to introduce differential forms into them now. So in the statement of Green's theorem, you have a subset of R2, D, it's an elementary region, and there's a boundary curve partial D, and typically we orient this counterclockwise. Suppose omega, which is p dx plus q dy, where p and q are both functions of x and y. This is a differential one form on some open subset of R3 that contains D. So D is a subset of whatever this set K is. Taking the conclusion of Green's theorem and rewriting it in terms of differential forms gives you the following. The integral over partial d of omega is equal to the double integral over d of d omega, or the derivative of omega. Recall before that the integral over partial d of p dx plus q dy equal the double integral over d of q sub x minus p sub y dx dy. If you take omega and if you take the derivative of omega, you get identically q sub x minus p sub y dx dy. I'll let you verify that on your own. It's not that hard to figure out, but you do indeed get q sub x minus p sub y, that whole quantity times dx dy. So we see that for Green's theorem, we can rewrite the integrands in terms of differential forms, or a derivative of a differential form, and we see that the integral over the boundary of a differential form is equaling the double integral over the interior of that region of the derivative of that differential form. Let's move on to Stokes' theorem now. Stokes' theorem, we have an oriented surface S in R3. It has a boundary curve partial S, which is a simple closed curve, and we work with the usual counterclockwise orientation. Suppose omega is a one form on some open set K that contains S. Then we see, rewritten in terms of differential forms, the integral over partial S of omega is equal to the double integral over S of d omega. So again, the integral of a differential form over the boundary is equal to the double integral of the derivative of that differential form over the interior of that region, over what's inside of that boundary curve. Now, in this case, we don't explicitly state what this one form omega is, but you can probably guess that the one form omega that we're talking about is the one form that's in the conclusion of Stokes' theorem, namely capital F hat dr hat. And if you think back to the conclusion of the Stokes theorem, it says that the integral over partial s of f hat dot dr hat is equal to the double integral over s of the normal component of the curl, or nabla cross f hat dot n hat d capital S. And if you take the one form that we're talking about here, if you take f hat dot dr hat, and if you write it as a differential one form in terms of dx, dy, and dz, if you take the derivative of that guy, you will come up with the curl of f hat dot n hat d capital S. Now, there's a specific reason why I'm not explicitly stating what the differential one form is here. There's a reason why I'm not saying what f hat dot dr hat is in terms of dx, dy, and dz. A little bit of foreshadowing there. Let's move on to the divergence theorem. Divergence theorem, W is an elementary region that's a subset of R3. It has a boundary surface, partial W, and we go with the typical outward orientation, the outward unit normal. If omega is a 2 form on some region K that contains W, then in terms of differential forms, what the divergence theorem is saying is that the double integral over partial W over the boundary of this region of omega is equal to the triple integral over the interior of that region, triple integral over W of d omega. And just like with Stokes' theorem, we're purposely not stating what this omega is. We're purposely not stating what this 2 form is, but you can guess that what we're talking about is the 2 form that's in the conclusion of the divergence theorem, namely capital F hat dot n hat d capital S. And once again, if you take capital F hat dot n hat ds, and if you write it to be a 2 form with dx dy, dy dz, and dz dx, then if you take the derivative of that guy, you will come up with the other part in the conclusion of the divergence theorem, which is the divergence of your vector field, capital F hat, times dx, dy, dz. You can give the component functions of your vector field names p, q, and r. And if you write p times something plus q times something plus r times something, differentiate that thing, that is your d omega, and that will get you to the divergence of your vector field. But again, just looking at the conclusion of the divergence theorem here, you should be picking up on the same thing, the same type of thing as what's going on in the previous 2 theorems. You see that the integral of a differential form over the boundary is equal to the integral of the derivative of your differential form over the interior of that boundary. So that is a big thing here. That is the key thing that we want to keep in mind. We can see that all of these conclusions, when we put them in the language of differential forms, they're almost identical. The only difference is what dimension are we working in. For Green's theorem, we're working in 2D. In Stokes' theorem, we are working in 3D, and in divergence theorem, we're working in 3D as well. But between divergence and Stokes, a little difference there in terms of single integral versus double integral, and double integral versus triple integral. So we're going to state the one big theorem now that sort of encompasses all of these guys. But we need to introduce some terminology first. And this is very technical for the purposes of our course, not necessarily something that you need to really concern yourself with. But if you're going to go on to take a higher mathematics course in topology, then these are some terms that you may want to keep in your mind and get more familiar with. So when we talk about an oriented two-manifold with boundary in R3, all we're talking about is a surface in R3 whose boundary is a simple closed curve with the usual counterclockwise orientation. So basically we're talking about Stokes theorem kind of thing here. We're talking about that part where we have a portion of our surface enclosed in some simple closed curve in R3. An oriented three-manifold in R3 is just an elementary region in R3 whose boundary is a surface with the usual outward orientation. So this is taking us back to the divergence theorem. Now, we're going to finally state the big master theorem. Here it is. It's called the Generalized Stokes Theorem. Let M, capital M, be an oriented K manifold in R3. For our purposes, K is usually 2 or 3, contained in some open set K, K being a subset of R3. Suppose omega is a K minus 1 form, a little k minus 1 form on our open set capital K. Then the integral of the differential form around the boundary of the manifold is equal to the integral over the manifold itself of the derivative of our differential form. We're finally there, guys. We've reached the granddaddy theorem. We've finally gotten where we wanted to get to. This is the theorem that connects every big theorem that we've talked about in this course as well as in earlier courses as well. So we've finally gotten there, guys. We've hit the main goal. Now, a couple small notes on the generalized Stokes theorem. As written here, you see there's just one integral written on each side. Well, they are to be interpreted as single integrals or double integrals or triple integrals wherever it is considered appropriate. So if you are looking back at Stokes, say, the left hand would be a single, and the right-hand side of this equation here would be a double. If you're looking at the divergence theorem, the left-hand side would be a double integral, and the right-hand side would be a triple. So writing one integral sign here in this theorem doesn't necessarily mean it's a single integral. It varies based on the context that you're in. And although we stated in here that K is 2 or 3, so 2 manifolds or 3 manifolds, this form of Stokes theorem generalizes to arbitrary dimensions. So K can be 4, 5, 6, 7, 8, even higher. But for our purposes in our course, K is 2 or 3. If you go on to take a higher level math class, then you will see cases where you use this for manifolds with higher values of K. So we finally come to the end, guys. This is it. This is the big theorem that ties all of our other theorems: divergence theorem, Stokes theorem, both forms of Green's theorem, the fundamental theorem of calculus, the fundamental theorem for line integrals as well. All of those guys are just special cases of this one theorem right here, the generalized Stokes theorem. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.